Hello, welcome back. This is Calculus by Dr. Oz. I'm continuing covering Chapter 2 sections, and Chapter 2 is all about limits and their properties. And today we're going to cover 2.4, which is continuity and one-sided limits. And continuity has a very cool application, and if you look at the upper left corner, you can see the Great Hadron Collider, and there's the Charles law relating the temperature of gases to their volumes, and there's a cool way of obtaining the absolute zero in Kelvin scale, and there's a very nice application of continuity using these concepts here, and if you're interested, please check that out in the textbook. We have 4 course learning objectives, and each of them is going to be a video. And first, we're going to start with the definition of continuity at a point, and as well continuity on an open interval. We are going to also discuss about the cases where the continuity fails. Informally, the definition of continuity is that if you say that a function is continuous at a point, that means there's no interruption in the graph of f at c. And you start from one point, and without taking your hand off, if you can graph the function continuously, then we call this function continuous. So in other words, the graph of the function is unbroken, and no holes, no jumps, or no gaps. And this is the informal way of saying that the function is a function is continuous. So in this slide, I'm going to demonstrate you 3 different cases where the continuity fails. Let's say like we have the open interval a and b, and the point of consideration is x equals c in each graph. And let's discuss about why the continuity fails in all of these cases. In the first one, the problem is that there's a punch at x equals c on the graph. So that means f is not defined at x equals c. So for that reason, since there's a break on the graph, or there's a hole, in other words, in the graph, so that makes this function not continuous. In the second case, we see that at c, the function is defined because it's filled here at c, as you see here, even though there's a punch here, but it's already filled at another value. So the function is defined. However, if you get closer to c from right, so that means you're walking in this direction. So that means the function values approach right here. If you walk on this direction, and if you get closer to c, and you can realize that the function takes another value here. So what that means is the limit does not exist. Even though the function is defined, limit doesn't exist. In fact, there is a jump here, as you see, from the bottom value to the upper value here. So for that reason, the function is not continuous. And then there's a break, obviously, if you want to graph this function with a pen and paper. And let's look at the last case scenario. Well, first of all, the function is defined because at c, it takes this value here, whatever that value is. Okay, and let's look at the limit of the function. So if you walk in this direction, and if you walk in this direction on the graph, you're going to meet whatever this point is. You're going to meet at that point, so that means the limit is going to be that value. So the limit exists. So the function is defined, limit exists. However, the limit value, as you see, let me just clean this up real quick. The limit value, which is right here, is not the same as the value the function attains at x equals c. For that reason, this function is discontinuous. So in each case, continuity at a point c is destroyed in the first case by having a function not defined at x equals c. And in the second case, the limit of f at c doesn't exist. And in the last case scenario, even though the limit exists and the function is defined, the limit value is not the same as the function value. For that reason, the continuity is destroyed. Here is the official definition of continuity at a point. We say that a function is continuous at c as long as all 3 cases do not happen. In other words, f is going to be defined at c, and the limit at c is going to exist, And the limit value is going to be exactly equal to the value the function attains at x equals c. And if all three conditions are satisfied, then you call that function to be continuous at a point c. Okay? And how do we define the continuity on an open interval? So you say that a function is continuous on an open interval ab when the function is continuous at each point in the interval. So you're going to check for each point that all three conditions are satisfied, and if you can check that for all points in the open interval, then you have the continuity on an open interval. And in general, if you want to show that a function is continuous on the entire real number line, which is minus infinity and infinity, that means at every single point the function has to be continuous. Take these all three conditions as the conditions of continuity, and we're going to sort of like refer back to that. So once the function fails to be continuous at a point, that means the function has a discontinuity at that point. And in fact, for all three cases, the functions are discontinuous at c. So the good news is that we can classify these discontinuities. We can classify them as removable or non-removable. Obviously, removable is sort of like better type discontinuity because you can redefine the function to make it continuous, even though originally it's not continuous at c, but you can redefine it at c so that the function becomes continuous. Let me explain that a little bit further here. So let's look at the first sample graph. Remember that f is not defined at c because there's a punch here. Okay, so I'm going to redefine this function by filling this hole up. So this is a brand new function, and it's a continuous graph from a to b, and now this function is continuous. So for that reason, f has a removable discontinuity at x equals c. Okay. For part b, well, f is defined at c, but I cannot redefine this function to make it continuous. Just imagine like you graph this function by a pen. There's no way to bring those two pieces together by just redefining the function value at c. I can redefine it here, 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 here even, or here, but there's no way to make this graph just one continuous graph all the way from a to b. Okay, for that reason, f has a non-removable discontinuity at x equals c. And in the last case scenario, f is defined at c as you see, and I have the limit value to be exactly equal to whatever this value is, okay, whatever this value is. So all I can do is to redefine the function so that it becomes continuous. So all I'm going to do, I'm going to move this value that the function attains at c and move it right here. I'm going to fill this up and get rid of this. Okay, get rid of this. So now I have a continuous graph. So all I'm tweaking here is just one value at x equals c, and if you can change it to something so that the function, the graph of the function is continuously sketched from point A to point B, then you're talking about a continuous function. For that reason, for this sample, f has a removable discontinuity. All right, I'm going to finish this video with 4 examples here. So in the first one, we have f of x equals 1 over x, and this was one of the examples we went through in the previous section. In fact, I had an animation of that for the question that was asking the limit of this function at x equals 0. And if you graph this function, and if you recall what I mentioned about it, you will see that when you get closer to 0 for x, and the function values either shoot off to infinity, right, or minus infinity. So at 0, left and right limits take you to different places, so there's no fixed limit value. In other words, x equals 0 is not even in the domain of the function. So for that reason, f is discontinuous, and I cannot remove this discontinuity by redefining this function because one side goes to infinity, another side goes to minus infinity. So x equals 0 is non-removable for this problem. And as a quick comment, this function 1 over x is continuous for all other x's, and 0 is the only problem point that is that function has a non-removable discontinuity. Okay, so let's look at the second function here. Second function is a rational function. I think we also had gone through this in the previous section. So essentially the problem point is x equals 1. Okay, because g of 1 is 0 or 0. Essentially 1 is not in the domain of the function. Just this one itself makes this function discontinuous. But let's try to see what kind of discontinuity it is. So if you want to graph this function, interestingly, so you have g of x, x squared minus 1 over x minus 1. And you can simplify this as, so if you factor the top out, so you can simplify this as x plus 1 as long as x is not equal to 1. Okay, x is not equal to 1. Okay, so when x is not equal to 1, it's a line, as you see, because g of x is equal to x plus 1, which is a line. So, and at x equals 1, it's not defined, so there's a punch here, as you see. This function is discontinuous, as I said, but you can remove it by redefining the function at x equals 1. So I can fill this up. Here we go. I have a continuous function, and I can redefine this function as I'm going to call that to be g twiddle of x. G twiddle of x is just x plus 1, and it's defined everywhere. So this function is continuous, as you see. So for that reason, x equals 1. The continuity at x equals 1, the continuity is removable. And let's look at part C. We have a piecewise defined function for non-positive x's. The function is defined as linear, x plus 1. And for positive x's, the function is exponential. So let's try to graph each piece, and the junction point is x equals 0, so we have to be careful on that. But I can tell you that if you graph this function, this is the linear piece and this is the exponential piece, and then they meet at x equals 1. And as you see that if you walk on this graph in this direction or in this direction, you're approaching 1, right? The limit value 1. So at 0, the limit exists, and the limit is attained, right? The limit L is equal to 1. That's exactly h of 1. So this provides us all the properties of continuity. All three conditions are satisfied. For that reason, this function is continuous everywhere on minus infinity and infinity. Okay, so continuous on minus infinity and infinity. All right, so let's look at the last function, and that's sine x. Sine x is a trig function, and it's defined for all x. And let's see what's going on here. If you graph this function, it's just a continuous graph. It's defined everywhere. So for that reason, this function is continuous on minus infinity and infinity. All right, this is all I'm going to say about this course learning objective, where in fact we first determine the continuity at a point by understanding how the continuity works. In fact, it's checking all three conditions I mentioned earlier. And we sort of like expanded that concept to the continuity on an open interval. Next, in the next video, you will see the definitions of one-sided limits and continuity on a closed interval. All right, I'll see you in the next video. Bye.